Welcome to the 6-4 lesson on applications of linear systems. Our objective: I can define variables, write a system of equations, and solve for said variables given a real-world scenario. Before we get started, let's do a quick review and remind ourselves that solving a system of linear equations can be solved with a graph, a substitution, or elimination. The best method is going to depend on the system itself, particularly the forms of the given equations and how precise your solution needs to be. And we have to remember, all systems could be solved using any of these methodologies, but some of those methods may require more work or more effort or have more potential for errors. And it's going to be determined by the characteristics of the system and kind of how it's set up. Systems of equations are useful for modeling real-world problems such as mixture problems, rate problems, and break-even points. Quick review of when to use each different method of solving a system. Graphing is really good when you want a visual display or when you want to estimate a solution, but you don't need to necessarily be super precise. This is particularly true when you're not given a graphing calculator or a graph. Substitution is really good when one equation is already solved for, or when it's easy to solve for one of the variables. Get x by itself, by just dividing by 2 or something relatively easy. Elimination is really good when coefficients of one variable are the same or opposites, or if they're not, it's relatively easy to get them there. It's also really good when things are lined up, so standard form is really good for elimination. Elimination is also a quicker method, so it might be better when it's not convenient to use graphing or substitution. So let's start off with the first of the types of problems, which is a break-even problem. Break-even points is a business term, and it's where the income equals the expenses, where the amount of money spent is equal to the amount of money made. If you look at the graph on the right-hand side, you'll notice a break-even scenario with a lot of information. So first off, let's notice that the y value, the y-axis, is the same. It's dollars. And for the red line, this is dollars spent on expenses. And on the blue line, this is your dollars spent on income. Your x-axis is usually number of items because you're trying to calculate how many number of items you want to sell or need to sell in order to break even or not lose money or not make money. So you'll notice where the red and the blue line intersect, that is the break-even point. There is some moment where you sell some amount of things and you have covered the amount of money that you needed to spend in order to produce those things. So anytime before the break-even point you have lost money, you're not in profit. And anytime after the break-even, you have made some amount of money. And so Y is used to represent both income and expenses. X is number of items, and left and right of that is going to tell you if you're in profit or in debt. The break-even point itself is infinitely small. It's for some amount of a single item. Maybe it's 200 hats or 500 dog collars or whatever it is. So no money is made or lost at the break-even point. And you could also think about it as money spent equals money earned. They're exactly the same. So break-even is kind of the infinitely small divider between losing money and making money. So let's find a break-even point. Let's say a fashion designer is making and selling hats. Material for the hat costs $5.50 and the hats sell for $12.50. Designer spends $1,400 on advertising. How many hats must the designer sell to break even? And at that break even point, how much money was spent and how much was made? Which should be the same number to give us a little bit of an idea of where we're going with this. So first, let's define our variables. Let's say X is the number of hats sold and Y is the number of dollars. Remember, this is expense or income because it's just dollars in general. So our expense equation, what did we spend? Would be the number of dollars equals 5.5 per hat because the material costs $5.50 per hat, and we spent $1,400 on advertising. So between the materials cost $5.50x and the advertising cost $1,400, we add those together. That will tell us the total amount we have already spent. Our income, the amount of money we get for selling the hats, is 1250 per hat, so 1250x. From here, we can choose any of the three methods to solve. They're both in y equals mx plus b form. They both have variables lined up, and they both have a variable solve for. So I'm going to use substitution here just because that seems like the easiest. So set the two sides equal. 5.5x plus 1400 equals 12.5x. Now it's just a multi-step equation with variables on both sides. Subtract 5.5x from both sides. Get 1400 equals 7x. Divide by 7. X is 200. So at 200 hats, we have broken even. Well, how much money do we have to spend to get to that 200 hats? If you plug 200 into either of the original equations, I did it both for both income and expense, you get y is $2,500. So when we sell 200 hats, which has cost us $2,500 to make and sell, we have made $2,500. So we are at net zero. We haven't made or lost money. At our 201st hat, we have made money. And at our 199th hat, we are still losing money. We have spent more than we've made. So exactly at 200 hats, we've broke even. We have not made nor lost any money. It's almost as if the enterprise didn't exist. Let's try another one. So we'll do another break-even point. Now we're making Sudoku puzzle books. Initial costs are $864. Binding and packaging of each book costs 80 cents. The price of the book is $2. So that's how much we're going to make per book. So how many copies have to be sold, and then how much money is needed to get there. So let's say X is the number of books and Y is the number of dollars. Our expenses, how much we spent to just make the thing to sell, is going to be the 864 of initial costs plus the 80 cents per book in order to bind and package it. Our income is going to be $2 per book, so it's going to be 2x. Again, because they're both equal to y, I'm going to use substitution. So 864 plus 0.8x equals 2x. Subtract 0.8x from both sides. 864 equals 1.2x. Divide both sides by 1.2, you get x is 720 bucks. So at 720 bucks, I have broken even. I've made back the money that I have spent. And how much money have I spent? Well, 720 plugged into either one of those original equations gives us $1,440. So at 720 bucks, I have both made and spent $1,440. I have not made or lost any money. So now that we're looking at real-world scenarios, we have to identify a new skill, which is identifying constraints and viable solutions. So in real-world scenarios, we need to understand constraints, where the equations seem to make sense, and then the viability of solutions tells us if those solutions make sense in the real world. Because remember, these equations, which are supposed to represent lines in a mathematical space, don't always equate to having meaningful value in the real world. For example, if you have a solution that has a negative number of hours, that's not viable because you can't have negative hours. Same thing for physical items. So if you have negative dollars or negative weight, it's a good sign that you don't have a viable solution. A good habit to get into when solving systems or real-world problems in general is when finished with a problem, ask yourself, does this answer make sense? Is it possible in the real world? So let's do a problem where we see the constraints and viable solutions. So local zoo, filling up 2 water tanks, elephant exhibit. One water tank contains 50 gallons and is filled at a constant rate of 10 gallons per hour. Second water tank contains 29 gallons and is filled at a constant rate of 3 gallons per hour. When will the 2 tanks have the same amount of water, and how much water will both of them have at that time? So let's go ahead and write a system, pick our variables. Let's say X is the number of hours the tanks are filling, and Y is the number of gallons in the tank. So tank 1 would be the 50 original gallons plus 10 gallons per hour, and tank 2 would be the 29 initial gallons plus 3 gallons per hour. And right off the bat, you might feel like this might not make sense, and I'll come back to that in 1 second. So because they're both equal to y, let's use substitution. 10x plus 50 equals 3x plus 29. Subtract 3x from both sides. 7x plus 50 equals 29. Subtract 50 from both sides. 7x equals negative 21. So go ahead and divide by 7. You get x is negative 3 hours. And right off the bat, it sounds weird to say negative 3 hours because you can't have negative time. Let's plug it in. to our original equations, knowing that that's not really a viable solution. But if you plug in x of -3 into both of those equations, we get 20 gallons. So what's going on here? Why does it feel, even from the initial writing of the equations, y equals 10x plus 50 and y equals 3x plus 29, that this isn't going to be a viable solution? Well, in y equals 10x plus 50, we're starting at 50 and then filling up 10 gallons every hour. In tank 2, we're starting at 29 gallons, but we're only filling it up at 3 gallons per hour. So tank 2 is starting out with less water, and it's filling up more slowly. So of course, the two tanks will never have the same amount of water in them. We're not even looking at, the maximum volume of the tank and when they start overflowing. It's impossible. Tank 2 has less water, and it's filling up more slowly. It's impossible for it to ever catch up to tank 1. So how would it have a potential viable solution? Well, if we change the hoses that are filling up the tanks, let's say tank 2 is getting 29 gallons to start, but it's filling up 10 gallons every hour, while tank 1 had 50 to start, but was only filling up 3 every hour, then at some point we would have it. But these two lines will intersect at -3, 20. So in other words, in quadrant 2, but we can't have negative hours. When x is 0, when time is 0, when we start filling up the tanks, that's when we're looking at value. We're only looking at value in quadrant 1. It doesn't make sense to go into quadrant 2 and to have a negative amount of hours. Let's look at some very specific examples of moving through air and water. They're very common systems of equations style questions. So generally, in case you didn't know this, weather moves from west to east in a counterclockwise pattern. So not only does weather spin, particularly storm systems, but it also moves from west to east as it spins. Now, very generally, when a plane travels west to east across the United States, this steady west to east winds acts as a tailwind. It is pushing the plane from the tail, and this increases the speed relative to the ground because the wind is pushing it. If you're going from east to west, you're experiencing headwinds. The wind that is going west to east is now pushing into the head or the face of the plane. And because the wind is pushing in the opposite direction as the plane's movement, this decreases the plane's speed relative to the ground. Generally, we have the equation ground speed, how fast you're moving relative to the ground, is equal to the air speed plus or minus the wind speed. So how fast you're moving in the air plus or minus the wind, depending on if it's pushing you or fighting against you, will give you your ground speed. So very generally, all right, east to west is airspeed plus wind speed equals ground speed, and east to west is airspeed minus wind speed equals ground speed. This is not a one-size-fits-all system. Sometimes the wind does not behave in this pattern, particularly when you're looking at that counterclockwise rotation. And so instead of remembering east to west and west to east, just think about tailwinds push you, headwinds hold you back, because headwinds are pushing into the head of the plane, and so it's slowing you down. Let's look at water. Generally, water flows downhill due to gravity, and that always happens. Water is always flowing towards a lowest point because gravity is pulling it downwards. When you're in a boat and traveling downstream, so the water is moving down the stream with gravity, the boat is moving in the same direction as the water flows. So the water is going down the hill, and so is the boat. This increases the boat's relative speed because not only are you pushing through the water at the boat speed, but the water is also moving in and of itself, so you add those two speeds together. When you're going upstream, the very common example we're taught about in school is salmon swimming upstream. That's when you're moving opposite the direction of water flow. The water's going downwards, you're going up, and so you're fighting against the water current. Because you're fighting against it and it's moving in the opposite direction, it decreases the boat's relative speed. So your total speed, how fast your vehicle, in this case a boat, is moving, is going to be your vessel speed, how fast the boat is moving within the water, plus or minus the water speed. So if I'm going upstream, Then I'm subtracting the water speed. And if I'm going downstream, I'm adding in the water speed. So remember, upstream, you're going up against the water. So let's solve a wind or current problem. Let's say we have travelers going from Charlotte, North Carolina to Los Angeles and vice versa. The airspeed of each plane is the same. So the planes are moving at the same speed if you were to put them in a vacuum. The ground speeds are shown on the map. What's the airspeed? What's the wind speed? So you can see Los Angeles flight moving 550 miles per hour. And we're going to Charlotte's, and then the wind is traveling from west to east like normal. And then the Charlotte one is going from Charlotte to Los Angeles, but it is only going 495 miles per hour because that wind is pushing into it. So the plane from Charlotte is experiencing headwind, while the plane from Los Angeles is experiencing tailwind. So let's define our variables. Let's say A is the air speed. So how fast the planes are going in the air, and W is the wind speed, the speed of the wind. So from California, because the wind is pushing the plane, A plus W equals 550. The airspeed plus the wind speed is 550. And from North Carolina, the plane is still moving at that same airspeed, but now the wind is fighting against it. So A minus W is 495. This equation set up nicely. Things are lined up. Coefficients or opposites are the same. I'm going to go ahead and add them so that my W's cancel, and I'll get 2A plus 0W equals 1045. So 2A equals 1045. Divide both sides by 2. A, the airspeed, is 522.5 miles per hour. So in other words, both planes, if I were to put in a vacuum or just measure how fast they were going without the wind, we would get 522.5 miles per hour. Well, what's the wind speed? You plug in that 522.5 into both equations or either equation for A, and you would get wind is 27.5 miles an hour. So the wind is adding 27.5 miles an hour to that 522.5 for the plane leaving Los Angeles, and it's subtracting away from the plane leaving from North Carolina. Will be our last question, and this would be a water-based question. So you row upstream, speed of 2 miles an hour, travel same distance downstream at a speed of 5 miles per hour. What would be your rowing speed in still water, and what's the speed of the current? So let's say B is the speed of the boat, and S is the speed of the stream. So if we're going upstream, our speed of our boat is going to be subtracted by the speed of the stream, the water. So I'm rowing at some speed, and the water is fighting against me because I'm going upstream, and I'm only going 2 miles an hour. So B minus S is 2. But when I go downstream later on, I now am going the same direction as the water, so my speed plus the speed of the stream is equal to 5. So I'm going a little bit faster because now the water is going with me, not against me. Again, things are lined up. Let's use elimination, but this time let's subtract, so get rid of the b's. So you have b minus b is 0b, negative s minus s is negative 2s, and 2 minus 5 is negative 3. You have the equation then 0b minus 2s is negative 3. 0b is just 0, so you get negative 2s equals negative 3, divide by negative 2. S is equal to 3 over 2, which is the same thing as 1.5 miles per hour. So the speed of the stream is 1.5 miles per hour. If we plug it in for upstream, the speed of our boat minus 1.5 equals 2. So how fast do we have to be going if we add 1.5 to both sides? The speed that we are going is 3.5. 3.5 minus 1.5 is 2. We're rowing at 3.5 miles per hour, but the water is slowing us down by 1.5 miles an hour, giving us a net of just 2 miles per hour upstream. When we go downstream, our equation is b plus 1.5 equals 5. Subtract 1.5 from both sides, you get b equals 3.5, which is what we expect because the other one was b equals 3.5. Here, again, we're rowing at 3.5 miles an hour, but now the water is pushing us an extra 1.5 miles an hour, so we're adding them together to giving us a net of 5 miles per hour.